Good morning class and welcome to another lecture in sustainable energy technology. In the last class we finished our discussion on wind energy. Today we will start on the next important class of renewable energy technology which are based on using solar energy as the source of energy for generating heat, electricity or useful work. Now solar energy, many of you have heard of solar cells, solar heaters, etc. And these are all different ways by which solar energy can be harnessed to produce useful work, electricity, heat. It's one of the most promising sectors of renewable energy technology, and it's also one of the most fastest growing. But before we discuss in detail some of the major technologies that are in use today for harnessing solar energy, let us start with an estimate of how much solar energy is available throughout the world, number one, and how does it vary from one place to another place with different seasons or with different hours of the day. So that will be the first section of our discussion about solar energy, the energy source proper, its availability, its variability, etc. So first let us look at this figure to the right. This is sun, this is earth. Okay, the sun is generating a certain amount of radiation energy through the diffusion reaction that is happening at its core. And this radiation energy is being emitted as electromagnetic waves that are expanding in a spherical circle around the sun as it leaves the sun's upper surface, and eventually it reaches the earth and a part of this radiation energy hits the earth's surface. Alright, so if we look at the earth and the sun and project a circular cross-sectional area which is facing the sun with respect to earth, the area of this circular cross-sectional area is equal to pi r square, where r is the radius of the earth. And the total radiation flux that is captured by this circular cross-sectional area is the total energy that is hitting the earth from the sun. Now the solar flux in terms of watts per meter square, that is the amount of energy that is incident on this circular cross-section area at the earth-sun distance per second per meter square, is around 1367 or 1361. So the values are slightly different depending on which decade we are looking at. The current values, the most recent values are around 1361 watts per meter square, and this is incident over a cross-sectional area of pi re square, where re is the radius of the earth. Okay, now of course this energy is being distributed over a hemispherical region which is the day side of earth. Alright. So this half hemispherical region, its surface area is 2 pi r square, and if you think of it on a per day basis, then on a given instant of time, the total energy, if you distribute it over the entire surface area of spherical earth, then that spherical surface area of earth is 4 pi r square, 4 pi re square. Hence, the average solar flux per unit surface area of earth is this S0, the solar constant, which is the flux at the earth-sun distance, divided by into pi re square, this is the total energy, divided by 4 pi re square, which is the surface area of the earth. So once again, let's understand what is going on. You have a spherical, earth is a sphere. It is projecting a circular cross-sectional area as it is facing the sun, and all the energy that is flowing from sun to earth through this circular cross-sectional area is being distributed over the surface of the earth. The area of this circular cross-section is pi re square, and the surface area of Earth is 4 pi Re square. So the flux into pi Re square by 4 pi Re square is the surface flux of Sun's incident energy on Earth, mean surface flux, which is then S0 by 4, which is around 340 watts per meter square. Okay, it is a little bit more, little bit less, but average will be 340 watts per meter square. Now this entire energy is not available on the surface of the Earth. About 22% is reflected back by the atmosphere to space. So this 340 watt per meter square is coming on the top of the atmosphere. As it is passing through the atmosphere, a part of it is getting reflected back into space by dust particles, by clouds, etc. And that is around 22%. Okay. So the radiation reaching the surface is 88% of 340 watt per meter square, which is 265 watt per meter square. Okay. And this is of course over the entire Earth, which includes the day side and the night side. So the illuminated half receives double this amount. Okay, that is around 530 watt per meter square. Of course, at night it does not receive any amount. So on average, it balances out. So what we can say then is that on average, the day side of Earth receives 530 watt per meter square of solar energy. We will see that this too is unevenly distributed. The equatorial zone gets more, the polar zones get less. We will discuss that later. But overall, it's 530 watt per meter square over the day side and 0 watt per meter square over the night side. So over a 24-hour day, it's 265 watt per meter square. Now, this energy is not incident at a single wavelength. Sun is a black body at around 5500 kelvins, and so its energy is distributed over an entire spectrum of electromagnetic wavelength, which is peaking around the visible spectrum, which is around 500 nanometers. It starts from around 350 nanometers to 750 nanometers. 350 is kind of the blue side, 750 is the red side. Okay, so it peaks around 500, 450, 500, 550 nanometers, the yellow green region of the of visible light. And however, there are significant radiation that is also there in the ultraviolet zone here and in the infrared zone here. Okay, this black line is the idealized black body spectrum of a body at 5250 degrees centigrade, which is around 5500 kelvins. Okay, because we add 273 to it to get into kelvins. So this is the ideal black body spectrum, and you can see that the solar flux distribution with respect to wavelength in terms of watt per meter square nanometer is very close to this ideal black body spectrum. Now, this total flux is separated out into a yellow zone and the red zone. The yellow zone is the one that is being absorbed by the atmosphere, so it does not reach the Earth's surface. And the red zone is the one that is hitting the Earth's surface proper. Okay. Note, however, that the Earth's surface gets heated, and so it also has a diffuse emission. Okay, so part of the sun's rays that are getting reflected by the dust particles among themselves creates this shiny blue light of the sky that you can see all around, and that also gives some amount of diffuse radiation back towards the surface. But this red zone is what is directly hitting the Earth's surface from the sun. And there are certain basic values when you are thinking of idealized black body radiation. The energy for a given photon is given by E equals to h nu, which is hc by lambda, where nu is the frequency, and this is given by c by lambda, where c is the velocity of light and lambda is the wavelength. Okay, here the wavelength is in meters, here it's given in nanometers. Okay, the values of the speed of light c and h, Planck's constant, are also given. The radiation intensity at a given wavelength for a black body this value, these values for different wavelengths is given by I lambda equal to hc by lambda cube 1 by exponential hc by lambda kbt minus 1. This is watt per meter square nanometer. Okay. And these values, lambda is the wavelength, h is given by this one, c is the speed of light, T is the temperature of the black body, Kb is the Boltzmann's constant, etc. Okay. So given the temperature of the black body and given the wavelength you are discussing, you can get the values of I lambda from these expressions. Now, the main point here is this. On average, the surface of the earth is getting 265 watt per meter square of sunlight over a given day. Okay. So that is the energy that is available for exploitation by different solar energy technologies. Okay. Now, when we're thinking of a solar collector can be a solar cell, it can be a solar water heater. What its task is to absorb the solar radiation that is incident upon it. Okay. So how much solar radiation is actually incident upon the solar collector is an important criteria in figuring out how much actual energy it can deliver. Only if you know the actual solar radiation flux on the collector, you can evaluate how much output it is giving and hence get an efficiency. Alright. So here, suppose you have a horizontal ground. This is the normal to the ground. This is the sun here, and it is and the radiation is incident in this direction on the ground. So the angle between the sun's radiation and the ground normal is given by theta z, which is the zenith angle. So the zenith angle is basically giving you the angle between the solar radiation and the ground number, and it's basically the angle that the sun makes with the ground horizontal normal, the horizontal ground normal. Okay. Along with this, as we said, the atmosphere also refracts part of the solar radiation, and that part of the radiation comes hits the ground as kind of a diffuse radiation, which is all over the spherical shell of the sky. Okay. So the total horizontal radiation, so this makes an angle theta z, right? And the solar collector area is flush on the ground. So you can think of the ground as your the horizontal component of the radiation is this G star, the normal component into cos theta z. Okay. So let me just explain this a little bit clearly. So here, the sun's rays are coming in this direction, right? So if a unit normal surface was oriented perpendicular to the sun's rays, so this is 90 degrees, okay, so this is a unit normal surface, then the flux that is incident on this surface that is normal to the direction of the sun is G star. Okay. So, and now, however, the ground is at an angle with this surface, right? So this comes here and hits it here. This angle is theta z, correct? So what we can see here is that the area, this area is different from this area which is oriented normal to the surface, correct? And so the solar beams kind of spread out over a bigger area. So this is kind of the total area of this solar beam, and the area of this beam oriented normal to the surface is this length L, and when it hits the ground it spreads out over a different length, this one. Okay. So what happens therefore is that this length L1 and this length L2 are related by L2 equals to L1 cos theta. Okay. So the total energy available is G star L2. Okay. This energy is then divided into this value, divided by L1. Okay. Now L1 is L2 by cos theta. So this becomes equal to G star L2 by L2 by cos theta. So this becomes equals to G star cos theta. Okay. So the total energy that is present in this section gets spread out over this entire area, which is given by this length L1, which is given by L2 by cos theta. So the total flux per unit of the horizontal surface is G star cos theta. Okay. So that's the basic idea. So here you will see that this angle is theta z. So these values are theta z values. Okay. So that's how you get the horizontal flux on a surface where the zenith angle is theta z. Remember, if the sun is directly horizontal, then theta z equal to 0 and you will have G equals to G star, where G star is the flux for on a surface is oriented normal to the sun. Okay. And this is the additional diffuse flux that is coming all over the sky. Okay. And together you have the total horizontal flux. Okay, the horizontal radiation, the total horizontal radiation as is being discussed here. Okay. So the global horizontal irradiance, the total radiation watt per meter square hitting the Earth's surface in the horizontal direction is equal to the direct normal irradiance, which is the G star cos theta. The total radiation in watt per meter square directly incident from the sun on the horizontal surface, plus the diffuse horizontal irradiance that is coming from all over the sky.